All right, so in this section, we're going to be talking about binomial distributions. So before we get into the definition of a binomial experiment, I want to talk to you guys about what a binomial experiment is. To be a binomial experiment, basically it just means that you're going to have two possible outcomes. So an example of this is if a basketball player were up at the free throw line and they were to toss the basketball, either he makes it or he does not. So the probability that he makes it would be the probability of success, where the probability of missing it would be the probability of failure. So that's an example of either you're successful in what you're looking for, or you failed at what you're looking for. Okay, so looking at this definition, it says a binomial experiment is the probability experiment that satisfies these four conditions. The first condition states that the experiment has a fixed number of trials. In other words, we can count the number of trials. It's not we're not repeating it over and over and over again, thousands and thousands of times, without ever stopping. It does stop at some point, so we can actually count them. The second one is that there are only two possible outcomes of interest for each trial. Either it's successful or it's a failure. And there will be some times where even if it looks like we're looking for a failure, that would actually be considered to be a success. It just depends on what we're actually looking for. And I believe there's an example of this in the notes in here. Okay. The third condition is that the probability of a success is the same for each trial. In other words, these are independent of each other. So no matter how many times we do this, the probability of one thing happening is the exact same as the probability of the next thing happening, or the next thing being a success. Okay. And then the fourth one, the random variable x counts the number of successful trials. Okay, so x just represents the number of successful trials. We don't need to count the number of failures. Okay, so before we get into the definition of a binomial experiment, I want to go ahead and talk about some different notation that we're going to be using. So a lot of this notation we've actually used before. So for example, n represents the number of trials. Okay, so the number of trials that we've gone through. Okay, P represents the probability of success. Q is the probability of failure. And X, so your value, is the number of successes. Okay, and we'll get into an actual formula for this here in just a little bit, but let's go ahead and look at this example. It says determine whether the experiment is a binomial experiment. If it is, specify the values N, P, and Q, and then list the possible values of the random variable X. If it's not, we're going to explain why not. Okay, so it says you take a multiple choice quiz that consists of 10 questions. Each question, it has 4 possible answers, only one of which is correct. To complete the quiz, you randomly guess the answer to each question, not a good test taking strategy. The random variable represents the number of correct answers. All right, so we're going to go through this checklist. Okay, so it says the experiment has a fixed number of trials with where each trial is independent of each other. So first of all, this is a fixed number of trials, right? So we have 10 trials. Okay, so 10 questions. Each question has to be independent of each other. So what I answer on one of the multiple choice questions is not going to have an effect on the next answer. Each question has 4 possible, number 2, there are only 2 possible outcomes for each trial. either success or failure. So each of these have 4 possible answers, only one of which is correct. So either you're right or you're wrong. So yes, the second condition is met. Number 3, the probability of success is the same for each trial. Okay, if I wanted to say what the probability is of actually getting each of these answers correct, it would be the probability of X would be, well, there's 4 possible choices and only one of which is correct. So I would say that the probability of success is 1 in 4, or about 25%. Okay, so part 3 is met, and then the number 4, the random variables count the number of successful trials, and yes, they do. Okay, so this is a binomial experiment. So we can say that this is a binomial experiment. Okay, so the next thing it's asking for is to indicate what N, P, Q, and X are. Okay, so N is the total number of questions that we're dealing with. So in this case, N would be the 10 questions. So N would be 10. P is the probability of success, which we calculated right over here, right? And so the probability of success is 0.25. So the probability of failure, well, if we have 1 possible answer that is correct, then we have 3 that is incorrect. So I could actually either just say 3/4, or I could do the complement, right? So 1 minus 0.25, which would give us 0.75, or a 75% chance that you would incorrectly answer that question. Okay, and then your X variable, so it says the random variable represents the number of correct answers. So X represents the number of correct variables, right? And if I were to actually list what those are, so it's asking us to write the possible list of them. So it's either you get 0 correct, 1 correct, 2 correct, and we can get all the way up to 10 answers correct. Okay, so those are my possible variables for X, for getting the answers correct. So the possible ways that we can successfully answer these. All right, so let's go ahead and talk about the binomial probability formula. Okay, so in class, I will show you how to do this on the calculator, but in a binomial experiment, the probability of exactly X successes and N trials can be represented using this. So what I want you to notice is that in the middle here, that is a combination. So it's saying that we have N number of trials and we're choosing X. Okay, this second part is just kind of an expanded form of it. So remember that this is still in CX. Okay, we just expanded it. Okay, but this is what we're going to have to work on memorizing. Okay. All right, so actually, let's go ahead and go a little bit more into it. So sorry, this was the combination, right? So in other words, we don't care about order. We don't care about what order those successes are in. This second part, what I want you to notice, so we've got P raised to the X power Q N minus X. So what this means, let's say that we had the 10 trials up at the top, right? And we wanted to know what the probability of getting exactly 3 successes, okay? What this means is that I'm saying we've got the probability raised to the third the probability of success raised to the third power. The second part here is actually going to be the probability of success raised to the other power. So in other words, what I'm saying is I have 3 successes here, which means that out of 10 trials, I have 7 failures. So these top 2 numbers have to add up to be your number of trials. All right, so let's go ahead and take a look at an example. All right, so before we actually get into looking at using this equation or this formula, let's go ahead and take a look at this example, and we'll do method 1 using tree diagram and the multiplication rule. All right, so it says a rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. We want to find the probability of the surgery being successful on exactly 2 patients. Okay, so method 1 is to just draw a tree diagram, and this is a perfectly legitimate method, but there will be times where it takes forever to work these out. Okay, so when building this tree diagram, if I were to say the first patient, so let's go ahead and say that this first line is the first patient. So in the surgery, it was either a success or a failure. Okay, and then if I were to go to the second patient, again, it's either a success or it was a failure, right? And same thing down here. So if it was a failure first, then it could be either a success or a failure, okay? And then last patient, so the third patient, it was either a success, a failure, a success, a failure, a success, a failure, or a success or a failure. Okay, so these are my 3 patients. We want to know what the probability of getting exactly 2 successes would be. So if I'm following this first row, so this would be a success, success, success. So this would be 3 successes in a row. Then we could do success, success, failure. This would be success, success, failure. This would be success, failure, success, success, failure, failure. This last one, we have failure first, and then we have 2 successes in a row. So this would be failure, success, success. And then I'm going to let you guys fill the rest of this out with me. And we get this as failure. Okay. So we're looking at the ones that say that have exactly 2 patients that were successful. So in this case, the first one doesn't work because there were 3 successes. The second one does. The third one does. The fourth one does not. The fifth one does. And then you'll notice that none of the other ones do. Okay. So in computing these, what I'm going to do is I've got this would be the probability of success. So the probability of success is 90% or 0.9. I'm going to say that this is 0.9 times 0.9 times, and then we need to multiply by the probability of failure, which is 0.1. And when you do this, you get 0.081. Okay, and you'll notice that your probability of success, or the probability that this happens, actually turns out to be the same for all 3 of these values. So this would be 0.081, and then I do the same thing down here. This would be 0.1 times 0.9 times 0.9, which again gives you 0.081. Okay, so the probability of being successful exactly 2 times could happen here, here, or here. Okay, so what I'm going to do here is the probability of 2 successes would be 0.081 times 3, which gives us the probability 0.243. Okay, so the probability of a surgery being successful exactly 3 times, or exactly 2 patients, is about 24.3%. Okay, so we have about 24% chance that we'll have only 2 patients who have a successful surgery. Okay. Now, what about the binomial formula? Okay, so the binomial formula is up here. Again, I'll just rewrite it down here. So this would be probability of x is equal to NCX times p raised to the x power times q raised to whatever is left over. Okay, so we're looking for the probability of exactly 2 patients being successful. So we're going to say probability of 2 is equal to, we know that, so let's go ahead and list out really quickly what these factors are. So we need n, we need x, we need p, and we need q. Okay, so those are the only things that we're looking for here. All right, so n is, let's see, we're doing it on 3 patients, so n is 3. X is 2. P is the probability of success, so that's 0.9. And Q is the probability of failure, which is 1 minus 0.9, which is 0.1. Okay, so I'm going to plug these numbers in. I've got 3 choose 2 times the probability of success, so 0.9 raised to the x, so 2, times q, which is 0.1, raised to the n minus x, which is 3 minus 2, or you could just write 1. And I'm going to let you guys type this into the calculator, but again, when you do this, you get the exact same result as we got up here. Okay? So you choose which one works best for you. For small binomials, this first method works just fine. It does take a little bit of room. For larger polynomials, you're going to want to definitely use method 2. All right, so in example number 3, it says in a survey, the U.S. adults were asked to identify which social media platform they use. The results are shown in the figure to the right. 6 adults who participated in the survey are randomly selected and asked whether they use the social media platform Instagram. Construct a binomial distribution for the number of adults who responded yes. So again, we do need to ask ourselves, is it a binomial experiment? And yes, it is. Okay, so let's go ahead and pick out the parts that we need. All right, so we need to know n. N would be the number of people that we're choosing from. So we said that we're picking 6 people, so n is 6. The probability of success is the probability of people who say they do use Instagram, so that would be 0.28, which means that the probability of failure would be 1 minus 0.28, which is 0.72. So that's 0.72. And then we need to know what x's are. So x is these are our possible the possibilities on people saying yes. So either 0 people say yes, 1 person says yes, 2 people say yes, 3 people say yes, 4 people say yes, 5 people say yes, or it is possible that all 6 people say yes. Okay, so we need to figure out, we're going to construct a binomial distribution, and we're going to use this a couple of times. So my binomial distribution is going to look something like the probability distributions that we were doing in the last section. So I'm going to have x, and I'm going to have p of x. Okay, so your x's, just like what we are the ones that we wrote in the list over here. So it's 0, 1, 2, 3, 4, 5, and 6. Okay, so now we're going to have to actually calculate each of those values. Okay, so probability of 0, p of 0, is equal to, so in other words, nobody using Instagram is equal to, we're going to use that binomial distribution, or binomial equation. So that was, remember, it's p of x is equal to ncx times p raised to the x power q raised to the n minus x power. Okay, so it's the, we're using combinations, and then we're going to multiply that by the probability of success raised to the number of successes times the probability of failure raised to the number of failures. All right, so taking a look at p of 0, this is going to be n, so 6 c 0 times p raised to the number of successes, which is 0, times, sorry, I guess it's not p, it's 0.28 times 0.28 raised to the 0 power times 0.72 raised to the 6th power. I'm going to let you guys do this in your calculator, but this gives us 0.139. Then we get p of 1 would be 6 c1 times 0.28 raised to the first power times 0.72 raised to the, now we're subtracting 1 from 6, so we get to the fifth power, which gives us 0.325. P of 2 is 6c2 times 0.28 to the second power times 0.72 to the fourth power equals, and I got 0.316 for this one. Okay, and I'm going to go ahead and just rewrite what these are. So notice that the exponents on the successes are going up, and the exponents on the failures are going down as we increase x, or the number of successes. Okay, so the probability of 3 would be 0.164. I want you guys working these out on your own, but I will give these to you so you can check them. Okay, so the next one would be 0.048. P of 5 is 0.007, and the probability that all 6 people watch Instagram is next to nothing, so it's 0.000. I think the next one is like a 0.4 or something like that, 0.0004 or something like that. Okay, so in our distribution, this is the part that we want. All you're going to simply do is recopy those probabilities. Okay, so we've got 0 is about 13%, 14%. 1 is about 32.5%. 2 is about 32%. 3 is about 16%. 4 is about 5%. 5 is about 1%. And 6 is, there's almost no chance that all 6 people will use Instagram as their primary source of social media. All right. So using a graphing calculator, I'm going to show this to you on a separate example, or on a separate video. So hold off for this one. Okay. And then example number 5, it says using the formulas. A survey found that 17% of the U.S. adults say that Google News is our major source of news for them. You randomly select 4 adults and ask them whether Google News is a major source of news for them. Find the probability that, and we're going to break this down into 3 different parts. So the first one is exactly 2 say that Google News is their major source of news. Okay, so example, part 1, we're looking for the probability of exactly 2 people. Okay, so this is exactly what we did in that binomial distribution up above. So I'm going to say that this is, we're picking, I guess we need to pull out part. So P, the probability of success, is 0.17. Q is the probability of failure, so that's 0.83. N, so that's the number of people that we're pulling. There are 4 adults that we're randomly asking. And then X, since N is 4, then X would be 0, 1, 2, 3, or 4 adults. Okay. In this case, we're picking the probability that exactly 2 of them respond yes. So we're just focused on this one probability. Okay. So using that equation, so remember it's NCX, P to the X power, Q to the N minus X power. Okay. All right. So this would be 4C2 times 0.17 raised to the second power times 0.83 raised to the second power. And again, I'm just going to leave this to you to do in the calculator. So this would be 0.119. Okay, or there's about 11.9% chance that exactly 2 of them will indeed use Google News as their major source. All right, number 2. Now it's saying at least 2 of them respond yes. So we're saying the probability of greater than or equal to 2. Okay, so to find the probability of greater than or equal to, what I want to do is take a look at our possible x values. So greater than or equal to 2 would be 2, 3, or 4. Okay, so remember that the greater than or equal to is an or statement, which means that we're going to be adding probabilities. So what I need to do is I need to find the probability of 2 plus the probability of 3 plus the probability of 4. Okay. Using your calculator, and again, I'm just going to kind of skip a couple of steps here. What you find is that the probability of exactly 2 is 0.119. The probability of exactly 3 is 0.016. And the probability of exactly 4 is 0.001. Okay, so again, you do this portion on your own. I want to make sure that you can do this on your own, and I'll show you in the calculator in class how to do this on the calculator. Okay, and so now all we're going to do is we're going to add these together, and you get approximately 136. Okay. So about 13.6. So this would be 11.9% chance. This would be a 13.6% chance. So really, there's not a high chance that very many people will, that at least 2 will use Google News. Okay. The last part is saying what is the probability that fewer than 2 of them will respond yes. Okay, so the only numbers that are fewer than 2 are 1 and 0. And notice that these are your complement to what we found over here. Okay, so a much faster way to do this would be to say the probability of less than 2 is equal to 1 minus the probability of at least 2. Okay, so because we're using the complement, it's much simpler to do this, and we get 0.864, or about 86.4%. Okay, so that's our chance. Now, if you did not want to do this, okay, if you did not want to use a complement or you did not see the complement, you would have to say, you would have to do the probability of 0 plus the probability of 1, add them together, and you would still end up with the same outcome. All right, so here's where we're going to be using the table. And the tables, I went ahead and gave you the page numbers. It's at the back of your book on page A8 and A10. Okay, so from A8 to page A10. So it says about 5% of workers, so about 5% of workers ages 16 or older in the U.S. commute to their jobs using public transportation. You randomly select 6 workers. We want to know what the probability that exactly 2 use public transportation to get to work. Okay, and obviously we can use the probability here. So we could say probability of exactly 2 is equal to 6 C2 times the probability of success, which is 0.05, to the second power times the probability of failure, 0.95, raised to the number of successes, which would be, failures, which would be that, and you get something here. Okay, another way to do this, is to again pick out your parts. So N would be 6, X is 2, Q is 0.95, and P is 0.05. So picking out your parts and going to this distribution. So I gave it to you in the notes, but I also gave you the page number. Okay, so this is a binomial distribution table. Okay, so what you're going to do is you're going to start by looking at the probability of success. Okay, so the top row, this top row up here, hold on. This top row up here is your probability of success. Okay, so we're going to be looking for 0.05, so this one here, right? And I'm going to only focus on this column. Okay, then I'm going to look at the left-hand row where it says NX, and I'm going to look for my N value, which is 6, and then I'm going to look for my X value under that, which is 2. Okay, so I can go to 6, down to 2, and I'm going to kind of trace my fingers to where they intersect. And notice that they intersect right here at 0.031. So that is actually the probability that we would find if we were to type this into the calculator. So the table is a very quick way to do this. The only issue with this table is that the ends that they solve for only go up to 20. And so after that, you're going to have to definitely use your calculator or definitely do it by hand. Okay, so again, all you're doing is you're just kind of looking for the probability of success, the number of trials, and then the number of successes, and you're just going to kind of trace and figure out where those intersections are. Okay, so this could potentially be a much quicker way to do this and type it in the calculator over and over again, but I'll leave that to you to decide. Okay, all right. The last couple of examples, it says a recent study found that 28% of adults read read an ebook in the last 12 months. You randomly select 4 adults and ask them whether they read an ebook in the last 12 months. We want to construct a probability distribution for the random variable x, and then we're going to graph the distribution. Okay, and we'll graph it using a histogram. All right, so let's go ahead and pick the parts out. So n is 4, P is 28%, which means that Q would be 72%, and then X is this. It's 0, 1, 2, 3, or 4. All right, so let's go ahead and figure out what our binomial distribution is. Okay, so for my x's, and my p of x's, again, I'm just going to leave the actual calculations to you. So 0, 1, 2, 3, and 4, you get 0.269, 0.418, 0.244, 0.063, and 0.006. Okay? So building a histogram, okay, so we have on our x-axis, that's going to be the number of adults who read, so number of adults who read ebooks. Okay, and this is going to be the probability of that. Okay, so the number of adults that read ebooks, that would be 0, 1, 2, 3, or 4 adults. Okay, notice that my probability only goes up to about 42%. So over here, when I go up, I'm actually just going to go up by 0.1. So 0.2, 0.3, and 0.4. Okay. Now, let's go ahead and graph these. So the probability of 0 was 0.269, so just above the halfway point here. Okay, so I've got my first one. The probability of 1 is just over 4, just over 40%, so right there. Probability of 2 is just under 2.5, right there. Probability of 3 is just under the 10%, and then probability of 4 is almost non-existent. All right, so this is our histogram. That's all you got to do. Okay, so you're finding the probability distribution, and then you're going to graph it on a histogram as we did before. All right, so we're going to cover this quick example in class, but I want to go ahead and talk about population parameters. Now, these are estimates, and you're always going to be rounding these to 2 decimal places. Okay, so the population parameters of a binomial distribution can be simplified to this. So it says mu is equal to the number of trials times the probability of success. Sigma squared is the number of trials times the probability of success times the probability of failure. And then the sigma is the probability of, it's just the variance, the square root of the variance. Okay, so I'm just going to finish this example really quickly. We have n in this case, so it says in San Francisco, California, about 44% of the days are clear. We want to find the mean variance and standard deviation of the number of clear days during the month of May. So May, by the way, has 30 days in it. So it has 30 days. Okay, so N in this case would be 30. And by the way, it is going to ask us to interpret the results in this one. Let's see. Then P is going to be 0.44, which makes Q 0.56. All right. So in order to find the mean variance and standard deviation, all I'm going to do is I'm going to start with N, so 30, and I'm going to multiply that by P, or the probability of success, so 0.44, and that gives us 13.2. So the average number of rainy days is the average number of clear days in the month of May is going to be around 13 days. Okay, the the variance, so sigma squared, will be that number, so 13.2, and we're going to now multiply by the number of failures as well. So this would give us 7.4. Okay, and then finally, the standard deviation, which is the part that we really want. This is kind of a questionable. This is kind of a step to getting into the standard deviation. But the standard deviation is what we want. When we take the square root, so this is the square root of 7.4, you get approximately. And again, remember that we're having to round these to the first decimal place. So this would be approximately 2.7. So you've got a standard deviation of 2.7 days. So let's go ahead and talk about the interpretation, which is what we're going to use this for. So interpretation. Okay. So we will say that on average, there are about 13 clear days in the month of May. Okay, so, and we have with a standard deviation, so with a standard deviation of about 2.7 days. Okay. So this is the first part of the interpretation. Now, we were also asked to determine any unusual events. And what I want you to remember from here is that to be unusual, it has to be less than or more than 2 standard deviations away from the mean. So to be unusual means that we have plus or minus 2 standard deviations. So it's the mean plus or minus 2 standard deviations. Okay, so we will have to do a little bit of calculation here. So we know that our mean is 13.2 and our standard deviation is 2.7. So when I do this, I get that 7.8 or 7 days, less than 7 days, and more than 19 days are considered to be unusual. So less than 7 days, more than 19 days. All right. So this means that any more than 19 days or less than 7 days is deemed unusual. And that is all, hold on, unusual.